Okay, good morning. We are going to make this start now. Thank you very much for joining us to this workshop. Congratulations for surviving this very busy week for us. Well, this is our second workshop on human-aligned reinforcement learning for autonomous agents and robots. As you possibly have seen in our webpage, we are interested in reinforcement learning, of course, but particularly in this human-aligned aspects such as interaction with humans or human-in-the-loop learning, aspect of safety or safe agents in both sense, like avoiding damaging the robot, but also, well, avoiding harming people around or working with robots. Other aspects like explainability, also interpretability, and others like ethics aspect, theory of mind, and so on. Okay, so well, this workshop is organized by Tomen from Tigen University. We have online Miguel from University Andrés Bello in Chile. We have also online Sirigita from University of Michigan and Denver. We also have here Pamela today from Monash University. Myself from UNSW in Sydney. Okay. We are going to have today a very interesting talks. The first one, the opening talk is going to be by Georgia. It's already here. Thank you, Georgia. After the coffee break, we will have Matthew and Dana's talk. And in the afternoon sessions, we are going to have two more invited talks from AG and Pulkit. So I want to take the opportunity to say thank you to all the speakers for accepting our invitations. Additionally to the invited talks, we are going to be holding a discussion panel at the end. So a couple of invited speakers are going to be part of this panel, plus two other invited researchers. One is from Sony, Pablo Barros, and the other one is is a PhD student for Stanford. So we are trying here to have different opinions in a broader manner. No, people like working in research for already a while, but also people with the industry perspective and others from being a student in academia as well. And as well, we will have some contribution talks. These talks are going to be held just after the lunch break. Well, we received 10 papers. We accepted 10 papers. From them, we have selected 3 of them to be given an oral presentation. However, all the posters are going to be presented as well as posters. So we have here at the outside part the poster panel. So this session, the poster session, are going to be coupled with the coffee break. So please, when we go to the coffee break, grab the coffee maybe and come back to have a look to the poster and to discuss with the authors more details. We will also be giving a best paper certificate and runner-ups. That's going to be done at the end in the farewell and conclusion part. So stay, please, until, if you can, well, especially the poster authors. So this is the overall program. Anyway, you will find it in our webpage. So yeah. One additional thing, which is maybe not that clear here, well, because of the space, it's the technical committee that I would like to take the opportunity as well to thanks them for the help, for their help reviewing the papers. You will find their names as well in our webpage. Okay. And well, finally, I would like to mention that we have some endorsements from different technical committees, ICRA technical committees, the one in cognitive robotics, the one in machine learning for automation, and the one in energy, environment, and safety issues in robotics and automation. Particularly, the technical committee for cognitive robotics, well, they asked us if possible, if we can actually show the slide that you are seeing now. So they want also to promote broader their activities. So please, in case you have more questions about the technical committee for cognitive robotics, you can contact Alessandra Sciuti. You can see the email, her email here down in the corner. So yeah. Sorry, there are a couple of extra slides I forgot. Yeah, that's important thing because we are also planning to run a special issue. We have already submitted a proposal to IEEE Robotics and Automation Letters. This is currently under review, but we are quite positive that it's going to be accepted. We have already as well a conversation with them, so we hope that we can get accepted this soon. Obviously, authors' papers are going to be invited to submit an extension to this journal. So yeah, please be attentive because we are going to be sending possibly a follow-up email later on if we get this accepted. Okay. Also, we have a YouTube channel. We are in X, so well, the QR code that you can see there is the link for our YouTube channel. We had all the talks given in our first edition in 2021, sorry, in ICDL that time, ICDL EpiRob conference. So you can see there all the invited talks. So they were recorded and they are publicly available for you in case you want to join. Anyway, you will find us in YouTube or in X with HARL workshop. And now, yes, finally, we are going to have a social event at the end of this workshop. Just after finishing, we are going to be heading to the garden at Eating House. This is 10 minutes walking approximately, so it's not far. Anyway, well, that's the address. Anyway, we are going to be going all together. So yeah, but that's the link or the web address in case you want to write it down. One thing that I forgot to mention is when for the discussion panel, we have set up a Slido. In case you want to ask a question to the panelists, you can add the Slido from now on. So any topic that you want them to discuss, please let us know. We have prepared a few, but also we want to see what the attendees want to discuss with them. Additionally, in case that is there any question for any speaker, you can also use Slido. That's fine. It's set up already. But well, obviously, if you are here, you can come directly to the microphone. That's fine. Okay, thank you very much. With that, I think we are gonna move on to our first speaker. So our first speaker is Georgia. I just wanna shortly introduce you. Sorry. Okay, so Professor. Okay, so our first speaker is Professor Georgia. Well, she's a full professor of interactive robot perception and learning, HARL, and the DFG Emmy Noether research leader of the IROSA group at TU Darmstadt in Germany. Her research interests are robotics, machine learning, reinforcement learning, robot perception, and HRI. So over to you.
Should I take it down as well? Yes. Okay, so I directly plug in this. Let's try with this first. Hi everyone. Thank you for coming this early morning on the last day of ICRA. I know that many of you are tired or that you partied last night, but I think we still have very important things to talk about, especially when we are talking about creating robotic behaviors for working alongside humans, working with humans, or learning from humans. So I would like to talk to you today about learning safe and coordinated human-robot interactions. And I wished I would say that we have solved this problem and that we are making, you know, the amazing progress that we see with transformers, but this is not the case when it comes to human-robot interaction, physical interactions in particular. So a bit of motivation. My goal as a researcher is to provide personal assistance, and I think the impact of this is very clear if we see the trend of the aging population. So these are people that are aged over 65 years old, and you see that we are already close to the 2 billion actually case. And we have seen also that during COVID, we were lacking a lot of caring and nursing staff. And due to the fact that now, people can acquire knowledge and skills also from their homes, and they can, find higher paying jobs than doing, the difficult and sometimes, let's call it also dirty job of taking care of patients or elderly people. They prefer to find other jobs. Therefore, the seniors are left over at home, and we know how many people actually were isolated completely during the pandemic. So it is clear that we need robotic assistants. And the vision of these robotic assistants, we have, of course, depicted it in cartoons, like in Jetsons in the 60s, but also moving on in like Hollywood movies, where we would imagine that these robots can in a human-like manner, behave and look also. They can be able to perceive objects and humans in their environment, learn to do their household tasks and their assistive tasks, but also to adapt to humans. However, we don't have such robots yet, right? And the perspective of having these robots having close interactions with humans, I don't think it's very, very close, even if we have made advances with the deep learning and generative AI methods. Of course, you may ask, what is the system that we should be working on for achieving such a goal? And I think it's evident if you look at the Rosie robot that mobile manipulation is key for advancing the field of human-robot interaction when we are taking into account physical interactions and assistance. Of course, they combine mobility and manipulability, therefore they can move around, interact with humans. They have multiple sensors which can augment their perception of the environment, and they have increased workspace. And also the fact that they are on wheels provide them greater stability, which also is related to safety from, a systems point of view. Therefore, I believe that this is the best system to work on when we are talking about human-robot interaction. But still, how do we learn, and how do we combine data-driven methods with, these systems in order to guarantee some sort of safety? It's non-trivial and it's not solved. No, so one of my research directions, or the core actually research direction, is to structure robot learning methods so that we can actually make improvements in the way that we learn. Of course, we know what robot learning is here, but what I mean by structured robot learning, it means to take into account the structure of the problem to enable faster, safer, and more scalable even learning of robotic behaviors. And I don't restrict it necessarily in reinforcement learning, and you will see during the talk there will be aspects of reinforcement learning, and in particular about safe reinforcement learning. However, when it comes to physical interaction with humans, you will see that we have not taken this leap yet of taking the next step of doing, for example, exploration among humans and tackling physical interactions. So what we are going to talk about, we're going to talk about how we can coordinate the robot, both as a mobile manipulator, so you will see some techniques, some algorithmic techniques that we have developed that you could imagine that we could actually use in order to transfer knowledge and coordinate interactions if we want to take this leap of doing reinforcement learning for human-robot interaction. We're going to talk about safety, so how do we progress towards safe learning, safe human-robot interactions with reinforcement learning. And finally, I will discuss some of our recent works where we learn fluent interactions, and all these three components as a key idea, how do we take advantage of structure, of the problems, of the models, etc. So the first question that we are going to ask is, how do we coordinate these mobile manipulators, because they have their multiple embodiments. So a couple of years ago, we introduced a work that actually works quite well. And I was very happy to see that it was picked up also by other groups, extended it with perception, but we are also obviously working on it. But I'm not going to talk about mobile manipulation so much. I want to focus mostly on the technique, the reinforcement learning technique that we introduced, that I believe it is more interesting for you. So let's take a look at mobile manipulation. Mobile manipulation has been traditionally tackled in two ways. Either you decouple the robot with some handcrafted objectives and you say, where do I move the base, then tackle it as a navigation problem and then trigger manipulation, or you try to do whole body control. The problem with whole body control is that it is an optimization framework, has a lot of local minima, especially if you consider external collisions, etc., which is also the problem if you consider interacting with humans. And it also doesn't have this look-ahead behavior. It doesn't know what is happening into the future. Of course, you could, again, consider, okay, you may do planning, but this entails knowing the dynamics of the problem, which is, again, extremely difficult when we are talking about human-robot interaction. So let's take a look at a simpler setting. We took a look on the first case where we decoupled the robotic embodiment, but this was made on a purpose. We wanted to give to the robot the opportunity to understand its own space, its own embodiment with respect to its environment, so that it also decides on its own, how do I move in order to approach something? How do I move? When do I know that now the manipulation skill can be initiated? And this could be also a whole body manipulation skill. It doesn't matter, because you want to take into account the manipulability of the robot with respect to its environment. So we are talking about a hybrid actions, decisions here, hybrid decisions, where you have continuous actions that are describing the optimal base pose in SE2, so position and orientation of the base, and also a discrete variable that very naively would say, should I activate my arm? But it could also be, should I activate this skill or not, in order to interact now with the environment? And how do we learn now? How do we do reinforcement learning with hybrid action? So there are many different techniques. However, usually what you see is either that you collapse between experts, and we took a different approach. We really wanted to inject this hybrid action space into the core of the problem, inside the policy. So we created a discrete action policy that explicitly describes this discrete decision variable of activating or not the arm. And if you think about it, this action, this discrete action, is conditioned on the continuous action. So if I am standing here, I will not be able to reach the tablet there, but as I am moving closer, I can already see when, okay, now I have enough reachability or manipulability when it comes to manipulation. So we have this probabilistic framework that allows us to basically combine these continuous and discrete parameters. The discrete can be modeled as a categorical distribution, which also gives you the possibility to have more than binary decisions, which is something that we hopefully will publish later this year. And in order to train this model with this categorical distribution, we have to do some tricks, because obviously you cannot backpropagate from discrete variables. And we use this Gamble softmax reparameterization trick that allows you to take your favorite reinforcement learning algorithm like soft actor critic and train in an end-to-end way this kind of hybrid problem, instead of having an hierarchical problem, which comes with issues, hierarchical reinforcement learning, when you have to take a discrete decision, wait for the continuous action to finish, and then trigger back a different discrete action to be triggered. So this is a more coupled problem. Yet we described the action space, but we now want to understand how to train this. And I've been talking about reachability, the robot understanding its own body. So we took a look about how we can take advantage of the robot itself. The structure of the robot itself can tell you a lot about the information about what is reachable or not. So we stepped back and looked at the older literature in mobile manipulation, where people would take the operational workspace. This is pretty easy to do in simulation. You sample millions of configurations in SE3, and then you run multiple times the IK, you also compute the manipulability index, and you create basically a volume that gives you some sort of frequency of manipulability. So if you are there is high manipulability or not. If you now consider the floating base scenario, that basically the robot can be anywhere in the world, and you invert this mapping and you cut it on the level of the floor, of the ground, then you can find the potential poses that the base of the robot should be placed in order to, for example, in this case, reach this 160 pose. And if you can imagine now, this is a very discretized problem. It doesn't necessarily generalize very well because it assumes that you have stored all these 60 poses, and somehow when you need to interact really with an object, you will have this information. So we said, why don't we take now this information and do offline training of this previous policy that I was describing, right? Then you will take a smooth Q reachability map, and we also explicitly designed the reward function to account for the success of actually reaching the target, not just, this is not even probability that you see, it's just a frequency, it's a frequentist metric. And what you see there is a completely different map that gives you almost 100% success rate for any pose, even if you have not seen it in the data set before, because you interpolated the space. But okay, still this reachability is very local. It only says to the robot, if I am here, what is the next step that I should do in order to do a manipulation task. And mobile manipulation and human-robot interactions in the environment are quite long horizon. The robot has to navigate, take things from one place, reach, for example, for a human, and then do a handover. So how do we take this information and transfer it to more complex scenarios? So in this case, we introduced a method called boosted hybrid RL. Hybrid because of the hybrid action space, and boosted because we used a technique that it is very known in machine learning, the concept of boosting, so using weaker, basically approximators, and we extended this to deep reinforcement learning. So what does boosting do? Boosting actually creates residuals on the Q function space instead of just learning residuals on the policy space. And we have actually showed that learning residuals on the policy space, it's quite bad. So what happens on the critic updates? Let's say that you have your task 0, that it is the one on the upper part here, and it was this reachability prior that we trained. Then the next task that could be, for example, just navigate and go to reach a target, so this longer horizon, navigation plus manipulation problem, you don't need to train your prior, you just need to add this row phi1, that is what you are missing in your Q function in order to understand how to complete this new problem. And this can be actually extended into multiple additional residuals when you are transferring to a more complex task. And also you can see that apart from that, a bonus on the actor by adding the KL with respect to your previous policy would actually accelerate the learning. And why this framework is also very nice is because it allows you to handle changing observation spaces. So you may start by having just reaching tasks, and then maybe you have to avoid obstacles and grasp something, and this can be represented into your action space, into your state space, while your prior may not have this information. So as long as the state space doesn't shrink compared to your previous or your at least your basic first task, you can still keep playing around with mixing these approximators. And it really makes a difference when you are doing transfer. You can learn very fast. So we started in simulation, and we just started with this local reaching, started navigating, adding obstacles, adding more constraints, and also testing how the robot can really find the reachability inside, on a table where only one object is the one point of interaction, while the others are considered obstacles in a more confined space. And what is also interesting is the fact that the way that we do reinforcement learning here is in some sense on a higher level of abstraction. It gives you where the robot should be next in order to see whether it has to manipulate an object or not. Therefore, how you will reach this goal, it's basically up to you which kind of policy you're going to use. You may use whole body control, you may use just navigation. And you can also combine it with pick and place and do rearrangement tasks sequentially, because once you know your own body and your reach with respect to the world, you can also combine these, the maps, basically these Q function maps do not change. The only difference in the success rate that we did is that we noticed that we used a different navigation policy in simulation versus in the real world, and this affected. But other than that, you could transfer directly because you don't apply directly reinforcement learning on the torques, basically, of the robot. But of course, this is the work that I presented to you right now allows you to train priors and then transfer them to more complex tasks. But still, when we are talking about human-robot interaction, exploration is a very difficult problem, and we know that we cannot really do exploration in the real world. So we have to figure out what kind of knowledge can we extract from interactions, from the environment, what is the representation that we want to use in order to also build up constraints. So again, last year, or a couple of years ago, we worked on neural representations, and we keep working on this direction, where we extended deep SDFs, deep signed distance fields, into a neural network that can basically represent the distance function of an articulated object, like the robot itself or any human, by also seeding the pose of the robot or the human in particular. We also additionally added some regularization techniques that would allow us to query with very high fidelity the signed distance function at any distance. And you can see, for example, when we go to the human in the lower line here, how nice, how nice our zero level sets are in the different planes compared to other state-of-the-art techniques. And what this allows us is when the robot, for example, is approaching a human that is doing random actions, is to query wherever you want this distance field and create basically your constraint in order to allow safe interaction till the point that the robot comes very close to the human, and then you need to collapse this safe space, if you want, for interacting with a human. Of course, you will see that we didn't do the handover still, because here you consider the human as one part, one object. Therefore, there is no discrimination between what is a contact point and what is not. But it is not even as trivial as I say right now, right? Because even if I remove, let's say, the hand for the handover from the SDF, still you don't want the robot to cross the hand, or I don't know if it is even making sense, we can discuss this later, to assume that the robot is going to be there holding an object and the human will just, put the hand exactly and take it out of the hand. But let's focus a bit on how, in the end, can we do safe reinforcement learning, especially if we want to impose constraints that are very, very, not relaxed constraints or like soft constraints into the problem, but rather, take into account the structure of these constraint functions. So we take an approach in which we formulate the problem of reinforcement learning. You can see your goal is to maximize the expected return, and you have several constraints. So instead of creating, let's say, a rough control barrier function that many approaches do for safety, not for so high dimensional problems as we will see in a while. And we consider the formulation of the robotic system. We can take the constraint functions and build the constraint manifold. So we can combine them, take this Jacobian, and then we can create basically the manifold and its tangent space. And what we do right now, once we have this constraint manifold and its tangent space, which is directly the null space of this, the Jacobian of the constraint function, we can transform the action space of the reinforcement learning problem such that it is always tangent on the constraint manifold, which means that you will never be allowed to explore and go away from the manifold in this case. So what we can do with this, we started playing around with navigation, where the robot has to take into account the differential drive constraints in this particular case, avoid this blue other agent, and also avoid collisions with the environment. And we can see that we can learn quite fast. So this was kind of a test bed. Let's see if it works case. But when we are talking about the real world, when we can perceive the environment, we want to actually create our constraints also kind of in the fly from perception. So I think these neural representations like the deep signed distance fields give us this opportunity to actually perceive, for example, an object, create its SDF, and then apply this safe reinforcement learning approach that basically changes the action space and makes you explore only on the tangent of the constraint manifold. And this is applied at all times. So it will be applied also just when you transfer in the real world without losing much of your capacity, because again, you are respecting the constraints, and you can also interact now with humans. What is happening here? What is the scenario? In this scenario, the robot has to deliver a cup to the human. Our student here is instructed to not look at the robot, look at its phone and just pretend that it's doing different things, like for example, reaching to get this orange that is on the table while the robot is reaching out, let's see it again. It's reaching out to deliver the mug. And if you think about it, if you are at your home and you are, I don't know, on your couch and on your tablet reading something and you ask the robot for, I don't know, a coffee, most likely you will just, do like something like this. Yeah, give it to me, I will take it. And you will not want to take care of the robot. You want the robot to have the intelligence to avoid the collisions and still keep the mug upward because you don't want it to be spilled around, right? So here we have trained. How did we do the training here? We have recorded interactions of humans doing actions, not this particular scenario. We have an additional scenario that I have not shown here in the slide. So we recorded human-human interactions with the OptiTrack. We collected we used the SMBL files in order to represent the human body, and we transferred this is the SMBL model, we transferred this in PyBullet. So we did different interactions, like I'm taking something for you, you take something from me, or I try to do a handover. So we collected a lot of human-related, interaction-related demonstrations, and we used those as our training environment. You would say that this is still an abstraction because we don't take into account the behavior of the human, right? The human, if I try to hit you and you see me that I am coming to you to hit you, the human would react. And unfortunately, this we are not able to model right now for such interactions. But it was good enough for the robot to at least understand volumetrically what does it mean for the robot to interact, and also to build in some sense kind of a prediction model of if the human does the arm like this, it means that I have to avoid it, but still maintain the constraint of not turning over the Mac. And yeah, we have done this several times. Initially, our student was quite scared, but then eventually saw that the robot never actually hit the human. So this made him more confident and did this interaction several times with the robot. But as I said before, still we have not performed the type of handover that we would really want to. To really come very close to your hand, exactly as a human with another human would do. And even if you touch the human hand, that basically it wouldn't matter. So we started looking more into, okay, how do we do physical interactions? What does it entail? And we know, and I'm sure many of you know, that being able to understand the intention of the other agent is very important for having good coordination, in particular when it comes to close interaction, like handshaking with another agent or doing object handovers. So we have quite long now a research line on this idea of coordinated interactions with the view of connecting it with the research that I showed you before. Unfortunately, there will be no reinforcement learning here because it's a very difficult problem. So I am happy to discuss with you how we could combine these approaches that I will describe right now with reinforcement learning. Let's consider the point of this human-human interaction, that it is just a physical interaction for handshaking. What are our requirements for coordinated and fluent human-robot interaction? We want the agents to react in a timely manner. We want to maintain physical proximity and also to be coordinated in the 3D space, right? It's not a simple scenario, the one that we are doing here. So in a work that was presented in 2022 in humanoids, but we later on extended and is currently under review for TRO, we introduced a method that combines statistical machine learning, like hidden Markov models, with variational autoencoders, this was a work where before diffusion models boosted all around. And our key objective was to discover modes and maintain them inside a variational autoencoder framework, because we know that variational autoencoders can very easily collapse into a single mode. How do we do this? So we have human-human interactions, and we build a framework through variational autoencoders where our goal is to, first of all, take the agent one, the one interacting agent, and try to learn its latent space based on a history of interactions. And we want to condition the other agent that will become later on our control agent to condition on the trajectory, on the latent of the previous agent, and to predict the evolution of the trajectories of this agent. How do we basically model this problem? We impose a hidden Markov model prior in the latent stage of this variational autoencoder, which allows us to learn the sequence, to discover basically the sequences of different modes. For example, now I am reaching, now I'm in the point of interaction, and now I have to break contact, for example. And we found this extremely useful, and we outperformed many other approaches that have to do with learning interaction dynamics in the end of the day. And how do we do inference? Then the only thing that you need is to take some history of the trajectories of the human, map them in your trained encoder into a latent space, and then condition the decoder of the other agent, that in this case is the robot, and extract possible trajectories on the joint space, and then perform also IK with some additional constraints on the optimization of the solver that we use. So we use optimization-based IK with additional constraints for safety to actually follow the trajectory and do the interactions. And here you can see an example of just the prediction, and you can see how on the right side the modes might change during the interaction in different scenarios from a data set from KTH, from Danica Kragic's lab. But we also collected additional data, so this is also controlling an agent, a YUMI. We found out that the space of interactions of the YUMI was quite weird, so we also collected additional data, and we open sourced this data set too directly from a camera. So we take from a camera and media pipe the skeleton of the human, and we tested it also in the real world. We also tested different behaviors, so having just IK by tracking the end effector, basically the hand of the human, our interaction dynamics without using this additional optimization through inverse kinematics and the additional constraints. But in the end, also with a large user study that we did, we found out that basically combining optimization and this latent space interaction dynamics is the one that gives the most friendly, let's say, perception to the participants. It is more timely and softer. Also, one point that I forgot to mention here is that given that we are able to discretize the modes and understand when the modes are changing, we are also able to change the stiffness of the robot. And so we don't do exactly variable stiffness, but we can actually change the parameters of the stiffness when, for example, the interaction is the handshaking to allow a more natural interaction with the robot. And finally, we want, our goal is to coordinate the robots to do this by manual, or not only by manual, but we want to take into account that we usually have in our minds that we are going to use bimanual robots, and we want to do handovers with these robots. So we extended the previous framework in an approach that uses a mixture density network. This mixture density network, again, introduces basically a mixture of variational experts. So on the latent space or a variational autoencoder, we learn different Gaussian policies and their mixing coefficients so that you can also combine them. So this is the power of this method compared to the previous one, is the fact that you can actually blend these experts that you discover in the latent space, and then you can again condition the robot and output the controls for the robot. The way that the training is done it's by trying to predict the motion of the human, but regularize it while you try to reconstruct the motion of the robot. But I will not take too much of your time. I will just show you some of the results. So in this particular case, we just again test the prediction abilities of these models to basically develop a latent space of interactive dynamics and how nicely we can see the change of the coefficients. And we also tested it for bimanual handover, but we also saw that it doesn't matter if it is bimanual or single arm, because even if your one arm is down and you interact with the other, the model is able to just interact with the type of hand that it is currently activated, regardless if it is the right or the left arm too. And I found it very, very interesting in this regard. And here are some limitations that mainly come from the fact that here we have not used perception. So many times through the optic track systems, the way that it was placed, we would not completely see the hands of the human. So sometimes the robot would not know if I reached basically the final stage for performing the handover, or would try to go backwards. But this was also very interesting, the fact that if you try to go towards the handover and then suddenly you decided that you don't want the object anymore, the robot would react and go backwards and just wait for you to extend your hand. But again, it needs some sort of filtering in between, some moving average, because if you just stand like this and you start moving your hand, this will be perceived like a motion and the robot will want to react. So this is kind of noise that we figured during the experimentation, but was tackled by just introducing some moving average on the trajectories of the human. So yeah, this concludes my talk for you today. As a takeaway message, I believe that we need to move towards more embodiment coordination also when we are talking about interaction with humans. I believe very much into this kind of scenarios required active perception. I didn't talk here about active perception, but in this conference we introduced a new method for active perceptive mobile manipulation that we want also to extend to human-robot interaction, because you want to actively perceive what the human is doing and basically build a model about what are the intentions of the human. I think I hope I convinced you about the need of neural geometric representations for safe interactions and how we can use them as constraints when we are exploring and learning, hopefully even in the real world. And finally, I showed you some methodologies where we can define structured priors for discovering multimodality, learning to sequence latent policies actually that they're not actually policies, they are latent models of these interaction dynamics that can be translated into policies that we could use into HRI, which I hope to use as a prior in a reinforcement learning framework, and why not the first reinforcement learning framework that I showed you. So train also IQ function alongside these policies that we are learning and use them in a transfer scenario to come to the real world and learn safely while interacting with humans. So yeah, this concludes my talk. Thank you very much, and I'm open for your questions.
Thank you very much, Georgia, for these interesting presentations. We have now some time for questions. We have now time for questions. In case you have one, please, you can come directly to the microphone.
Hello. Yeah, thanks for the nice talk. This constraint manifold that you had, can you explain a little bit how it works in practice? So if I am in some state with my robot and I have my constraint function, how do I get this manifold? And I guess here it's mainly coming from the kinematics of the robot, or could you also use it for some other constraint?
It can be any constraint. It could be any constraint that you, of course, you may. It could be also inequality constraints that you introduce a slack variable. You create the equality constraint. You combine all of them. Of course, they should all correlate to the Q, right? To the actual controllable state. You take the null space of this function that you have created, that it is basically the composition of all the constraints, and then you take the Jacobian and you take the null space of this Jacobian. And then you map your actions into the null space of this Jacobian function.
Yeah, I get that we want to go into the null space, but I'm not quite. Okay, maybe I just read the paper. Okay, thanks.
Maybe we can discuss it also later, more details. But we describe it in this paper, and there is also a previous paper on these where it's only constraints that regard the robot itself. And in this work, we extended it to also external constraints and considering more generic control-affine systems.
I have a question about your safety approach that you just showed us. Well, obviously, I would like to hear more about this particular case that you mentioned in which, well, a person or the robot need to pass an object to each other and how you are planning to do that. But before that, I have maybe a quick question, because I guess that the assumption there is that any time that the robot touched the person, that would be a safety violation.
Yes.
But I was wondering, well, you also have shown us some videos in the human-human interaction and so on. So maybe the robot would like to capture people's attention by just poke, because the person is, just to say a message, because the person is looking at the phone as you have shown, or maybe someone could be with headphone, whatever.
Yes.
So is there a way, or maybe that case would be in the same case for passing an object or so on?
Yes. So we are currently working on a method where we kind of create compositional distance functions, which we use actually there as control barrier functions, not exactly as constraints. So it's a more, a range in which you can be safe, while the approach that I showed today, it's a hard constraint, a hard transformation on the action space. So what happens in this case? You want to rely on some sort of perception in order to change what is perceived as a constraint or not, while maintaining some sort of safety. So what we are trying to figure out is how, for example, as you said, maybe I want to poke you here on the shoulder, but still I don't want to with my elbow. Maybe the robot, because also of the kinematics, comes like in a weird configuration, he does something here, nicely and softly, maybe with some impedance, while here you don't have very much, you have higher stiffness and you hit the human. So it is a matter of trying to understand what are interaction points and what does it mean, though, the interaction point for the policy. In that case, I hope we will have a work in a couple of months out on this point. We will basically do again a hybrid approach, that there is a part of the interaction that it is relying on known dynamics, on control barrier functions and so on, but there will be another part that it is a learnable part that learns just to allow the interaction in a safety manner. In all these cases, our biggest hurdle is the lack of simulations. We don't have simulations of humans, and we don't. So what we did there was actually very helpful for us. So we recorded humans, mapped their bodies into these SMPL models, put them inside pipe bullet and replayed the trajectory so that we can really not have skeletons of humans, because having just a human skeleton doesn't mean anything for when you want to safely interact physically. But if you don't model also the behavior of the human, you don't know what actions are actually permitted or not. And then one more point, because you are focusing on reinforcement learning. When the other agent starts interacting in a way that you don't know, it's obviously a partially observable problem. And it's actually quite a non-stationary problem, because you will never have the exact behavioral model of the human, and the robot will have to be able to generalize on many, many different situations, which makes the reinforcement learning problem and exploration extremely difficult. But I believe that transferring from priors is a very important point. So this is the first one. The very naive thing that you could do in this particular case, which we could have done, but we didn't because, time, was to just segment the body parts and just say, since here in particular we have very good tracking because of wearing the OptiTrack suit, I will just take off I will put the level set on these particular points into 0 and allow interaction there. But this will not guarantee, and you can do it with impedance, like You could combine it with what I showed later, that was the mode switching, so the interaction, and say, now I'm in the mode of the handover, and I will change the stiffness so that I have higher impedance to ensure that, okay, I'm coming, but I'm not coming also with very high precision, because you don't care for precision in exact precision in handovers. It's not a pick and place or an insertion task and so on. So I think that these are like techniques that you could do, but I don't know how this would be perceived by the humans. I don't know if it will be the same thing as two hands, and even touching you doesn't matter. The end effector will not have impedance, so it's another thing to consider from the overall design of the robots that we have.
Thank you. And regarding to the robot poking the person, I find really interesting this interaction point that you mentioned. And I was wondering if robot stiffness should be also taken into account in that sense, because obviously the stiffness you put on.
So as I said, right, so you could actually handle this in the discrete mode switching manner, right, that I am now in an interaction. So this hopefully gets detected by your latent model, and you have some parameters of stiffness that you change. The best would have been if, depending on the interaction point, the robot, the policy actually can modulate the stiffness directly, which is difficult because you don't know the range of values and the different scenarios. Again, the problem is the simulation there. So it is safer to say that I will have these parameters when I am trying to be very reliable in the motion, and these parameters if I switch into the physical interaction and I just want to give something or to poke or to do the physical interaction, there you can impose less stiffness basically.
Okay, thank you. We still have some time in case there is any other question.
Yes.
Thanks a lot for the talk, Georgia. My question's about the reachability function that you showed. So something tells me that it's inherently connected to the agents or the robot's transition dynamics. So is it something like kind of learning like a partial model or something like that, or?
It's so it's not related to the dynamics, but it is related to the differential kinematics, basically, of the robot, because you're taking into account the Jacobian, because you're computing manipulability. So it takes into account that whether I will have the opportunity to actually interact with an object. It doesn't take into account whether I am able to, for example, output the amount of force or like wrench into the environment in this particular case. Okay. But it is by, in some sense, encoding the kinematics of the robot, building like an understanding of like, oh, this is how I move. And the way that you train it with the reinforcement learning, because you always penalize also if the robot collides and so on, it kind of understands also volumetrically its own body. Yeah.
So in case you're midway through the operation, if the robot's hand gets jammed or something like that, that would directly affect the reachability. Right?
Yes.
Okay. Thanks.
Okay, guys, if we don't have any other questions, please join me to thank Georgia for her talk.
Thank you very much. Thank you for having me.
Remember now they have the coffee break, but in parallel we have the poster session. So please come join us, join the authors, and you can get more details about the presentations and the papers presented. We will come back at 10:30 here in the room with Matthew's talk.